Hello everyone, I'm Arek Nowakowski and I represent the team of researchers who has been working on the field of the grammar inference for some time. In this presentation, I'm gonna talk to you about a new tool for context-sensitive grammar induction. But before I dive into the tool's details, let me introduce our motivation and ideas. In terms of context-sensitive grammar induction, most of the operation has exponential complexity. This is one of the major obstacles in this field. So, it's easy to find out that it's hard to find any tool for finding a contextual grammar based on examples and counterexamples. In response to this conclusion, we've implemented a new tool for context-sensitive grammar induction from positive and negative examples and made it available to the community through public repositories. Now, we come to our ideas on how we handled a solution for the problem. Our main idea is to use genetic search for grammar inference. In order to do that, we have to define all required elements of genetic algorithm, such as the structure of the individual, the fitness function, genetic operators, and so on. I will explain this in details later on. But before we dive in, you can ask yourself how a randomized algorithm can bring a good grammar. We note that even an imperfect grammar could be available and useful when we have more such inaccurate classifiers. This approach is called ensemble methods, which is based on the observation that multiple classifiers can improve the overall performance over a single classifier if they are mutually independent. It's worth noticing that our implementation is written in F#. Hence, the library can be used with any language compatible with Microsoft.NET Framework. I've divided my presentation into 5 sections. We start with the structure of the library. Next, I'm going to explain all the details about our genetic algorithm implementation. Afterwards, some examples of usage will be described, as well as the availability of the library. Finally, I will end with quick recap. Let's look at the library structure. There are 3 modules: parameters, which are basically a data structure that handles settings for grammar induction and the genetic algorithm. The genetic algorithm module and so-called parsing module that handles data structures and operation for grammar decoding. Let's look now at the second module, which is the genetic algorithm module. As I mentioned earlier, in order to create a genetic search algorithm, we have defined the following 4 elements: the structure of an individual, the initialization routine, the fitness function, and genetic operators. Let's move on to the structure of the individual. We made an assumption that our main goal is to induce a grammar from samples in Kuroda normal form. Therefore, in our approach, an individual represents a grammar in Kuroda normal form. As the expected size of grammar, the terminal symbols, and the number of non-terminal symbols are given as a parameter of the algorithm, And as the start symbol is determined based on the actual values stored in an individual's data, in the result, an individual only decodes a set of the production rules. An individual has a form of array composed of non-negative integers. Each integer is an array represent a production rule. Let's see an example. Let's say that we have two non-terminals and have two terminal symbols. Then each possible production is associated with a number, so this production rules gets 0, index 0. This production rules gets index 1, and so on up to 31, which goes of course to the rule AA to AA. So as you can see, all production rules are coded with the non-negative integers, and we put them into an array that actually built our individual. Okay, next thing I'm gonna talk about is the initial population. The idea here is very simple, and it's about using a completely random initial population. Each individual is an array in which values are drawn uniformly from a center range. Additionally, I can say that the length on the array is parameterized by the k parameter. Okay, that brings us to the heart of all implementation of genetic algorithm. That is the fitness function. We have decided to use balanced accuracy. It was selected because we allow the number of examples and counterexamples to be substantially different. On the slide, you can see the formulation of the fitness function. Let's see. So we have some words that belongs to the set of the examples as well as the set of the counterexamples, and we count if this word belongs to the language that is defined by the grammar, which is encoded in the individual, or it doesn't belong as the counterexamples suggest. And all is divided by the sizes of this sets. So this is our fitness function for the grammar. As you can see, in this approach, the fitness function requires a high computational complexity. Consequently, in order to reduce the number of evaluations, we've used the steady state genetic algorithm, which will be briefly described in the next slide. The basic idea of steady-state genetic algorithm is to change the generation approach in classic genetic algorithm. The two major differences are in the selection and the deletion policy. In short, you can say that during the selection, a tournament is applied, in which the two best individuals from the randomly selected subset of the population become parents. Moreover, parents and offspring can coexist together in the population. After creating a new individual, it just replaces another individual in the population. Okay, let's look now at genetic operators. First, crossover. So, as we decode our individual as arrays, we made some functions to help understanding our crossovers. So we have head function from array that denotes actually the first element of the array, and tail from the array that denotes the remaining part of an array. Let's assume we have two arrays, x and y. To that end, let us consider 4 cases in the next slide given recursive procedure. Let's look at these 4 cases. Okay, so first case. If both arrays are not empty, then if the head of x is equal to the head of y, append head of x at the beginning of the result of the recursive crossover operation performed on the tail of x and tail of y. If head of x, we remember that the elements of those arrays are not non-negative integers, head of x is less than head of y, then with the 50% change append head of x at the beginning of the result of the, once again, recursive crossover operation performed of the tail of x and entire y. Otherwise, with the 50% change, append only head of y at the beginning of the result of the recursive crossover operation performed of x, now entire x, and the tail of y. The second case, if x is not empty array and y is empty, then every element of x has 50% chance to be copied. On the other hand, if array x is empty and y is not empty, then every element of y has 50% chance to be copied. In the last case, when both arrays are empty, then the procedure returns the empty array. What about the mutation, the second genetic operation? So this is a very plain, because mutation is during the mutation a randomly taken entry is changed, so entry in the array, to a new randomly generated value, and it's important that is not already presented in the array. So we put an entire new value that is not existed in the array. Okay. That brings us to the example. The code here is written in C#. Let's see. So as you remember the slide with the modules, the first module is actually the parameters, and we have some parameters for the genetic algorithm. We have some parameters for the grammar induction, and we have some other parameters for verbosing and the random generator to conduct more precise experiment or the repetitive experiments. And at the end of the day, we need to only run GA method with these parameters and give this as a certain output. Let's see the output. So in this case, as we put the verbose 200, so every 200 evaluation we get the best individual so far. At the end of the procedure, we get the final best individual, and below that we get, and this is what actually parsing module does, we get a final grammar with a precise score. So, and this is it. So it's from the perspective of developer, for the perspective of the programmer, it's a very simple API. All documentation are included in the on the GitHub and in the NuGet packet. So okay, so this is it. If we if we're talking about the programming things, so you can wonder how to download our work, how to download this library. So we actually recommend two ways. The first is a GitHub repository. This may be a hard way to receive it, yet you can actually download it and change it if you want it. But the most straightforward way is the NuGet repository, where this library is uploaded as a package that can be used in any .NET compatible programming language. You need to only search in the NuGet context sensitive grammar induction .genetic search. All the information as well as these links are included in the paper, in the article, so you can find it. And on the GitHub repository as well as in the NuGet repository, you can find full documentation for this library. So all these parameters are described, how what is the range of the certain values and so on. Okay, so that brings me to the end of my presentation. So recap all important information. The presented open source NuGet library for context-sensitive inference has been described. The library is written in F#, hence it can be used in any .NET framework language like F#, C#, C++, Clive, Visual Basic, and so on, and run under the control of varied operating system. The important feature of our GA routine is its non-deterministic nature, leading to the opportunity to achieve many different grammars that can be used in the ensemble methods. That's complete my presentation. It was a pleasure to talking to you. Thank you very much for your attention.